All right, I'll stop at 1 minute. 1 minute, still missing one person out there. I'm going to stop at 1 minute. Okay. Is it somebody that just waits until I stop? It seems like that way in every class. All right, C is the right answer. Very good. I know that in the bottom of the wing I have to have a bigger pressure, right? Otherwise you wouldn't get lift. So you have to have a high pressure in the bottom. So you can get rid then of options B and D. And according to Bernoulli's principle, if I have a small velocity, that means I must have a big pressure. Small velocity means big pressure. High velocity means low pressure. That doesn't make intuitive sense. Like you wouldn't really think that was the case, but it's true nonetheless. If I have a high velocity, I have a low pressure. And that comes about in the interplay in this equation. If V goes up, P goes down, or vice versa. Now number 3. A plane flies from low to high altitude at constant velocity. Which of the following is true? All right, I'll stop at 1 minute. Yeah, they are sort of all over the board. The right answer, they give the right answer as A in your book. I would disagree with it, but it says that at lower altitude the plane will experience greater lift, and it goes about because of this because of the Bernoulli's equation. That if H decreases, then P increases, right? But I don't believe that, because your pressure difference is the pressure difference between the top of the wing and the bottom of the wing, and so that H shouldn't have such a big deal on it. I'm going to list A as the right answer, but I don't think that's correct. It is more dense, yeah. So your density goes up. Right. Well, if your density goes up, though, if the density goes up, then your pressure should go down. And that's not what it's saying. It's saying that you are experiencing a greater lift. I don't know. Let's just leave it as it is. But that's good. Most of you got the answer. What they said was right. Okay. Let's try number 4. Airplane is encircling an airport with decreasing speed. When the airplane reaches point P, what is the general direction of its acceleration? This is a vector problem, which we've already seen. Think about the acceleration vectors and how many acceleration vectors there are. If you finish this, go on and look at 5 and 6. 5 and 6. Stop at 55. 55. Oh boy. Okay. Let's see. Some of you put A, some of you put B. All right, B is the right answer. How many acceleration vectors are there? There are 2, right. So we have the centripetal acceleration. The centripetal acceleration is towards the center of the circle. But then, since it says that it has decreasing speed, we also have another acceleration, the tangential acceleration, we'll call it, or the linear acceleration. So since the plane is moving in this direction, at point P, that acceleration vector is in that direction. And so the sum of those two vectors is in this direction. Andrew? Normally when we deal with circular motion, we deal with things that are not changing speed, but in this case it is changing speed. And when it's changing speed, that acceleration vector is tangent to the circle. Let's try number 5. Where's the pressure the highest? Think Bernoulli's principle and continuity equation, or the flow rate equation. If you finish 5, go on to 6. You can see up here, but right now it's open for 5. Stop at 35. 35. D, where's the pressure the highest? That's right, good. Why is the pressure higher there?
Is it higher point A or is it point dash? Which one is A? Because I'm not sure. Point B. I'm going to put point B. Point D, that's choice B. That's a trick question.
How is it a trick question?
Oh, wait. Are we on 5?
Yeah, we're on 5.
All right.
I already did the last question, but answering number 6 is answer.
Oh yeah, I'm sorry. It's number 5. But you still got the right answer. Many of you did. All right, 65% of you. So why is the pressure highest at point D here? The velocity is low, right, by the continuity equation, which says A1V1 equals A2V2. And so when my area goes up, that means my velocity goes down. And so that's the flow rate equation, or the equation of continuity, we call it. And then by Bernoulli's principle, if the velocity goes down, the pressure goes up. Right, so if the velocity goes down, the pressure goes up. Good job. Now let's try number 6. Run this one. What can be determined regarding the flow? Where is the flow? Is it highest at C or D? The flow cannot be determined, or is it constant throughout? All right, I'll stop at 42. 42. Hey, good job. Y'all know this stuff pretty well? Yeah, it seems like it. D is the right answer. It is. The flow rate is always the same. That comes about from the conservation of matter, that you can't have, a certain flow rate here and then more or less matter flowing here, because then you would be either destroying or creating matter, and that you can't do that. So D is the right answer. Excellent. All right. Let's try a few more. Actually, let's, everybody get the handout that I gave you? We might come back to this in a bit, or we will come back to it. I have some other problems. And then there's one more topic here. Yeah, of course. Anybody else need one? What its flow rate is? Flow rate is the amount of volume per unit time. For anytime you talk about the fluid flow, you're going to be talking about cubic meters per second, or cubic centimeters per second. All right, so this is the handout that I gave you. Let's try this number 565. This was a basic pressure problem. Remember, try doing it without your calculator. You know, guys, when you're working these problems, you'll want to look at your options because you might, when you think about this problem and sort of what roughly the pressure should be, one of these answers should jump out at you, that it has to be that answer. Or maybe it doesn't jump out at you. Oh, okay. I'm going to remind you of the equation. That is that P equals P naught plus or minus rho GH. Y'all are thinking too hard about this. Let me help you out a little bit. What is the pressure here? What pressure is pushing down right there? Atmospheric pressure. So I have 1 atmospheric pressure pushing here. Is the pressure here bigger or smaller than the atmospheric pressure? It's bigger, right? Remember what atmospheric pressure is? It's 1 times 10 to the 5th. 100,000 newtons per square meter, or pascals. All right, I'm going to stop at 310. 310. Just a few more seconds. Okay, good. So if you see that, you don't really have to do any calculation at all because you see that number D is the only one that's greater than the atmospheric pressure. It would only be if the level of the fluid here was, say, here, and then it came up. In this case, if it were like that, then the pressure of the gas would be less than the atmospheric pressure. And given these options, you'd have to figure out which one of those it was. All right, let's try this. Fully submerged solid sinks deeper into water. The buoyant force on the water does what? This is Archimedes' principle. If you recall, Archimedes' principle described the buoyant force. It was that the buoyant force is the density of the fluid times the volume of the object times the acceleration due to gravity. That's the weight of the displaced fluid. All right, about 10 more seconds. I'll stop at 1:15. What is C? Very good. It remains the same. So there is a minor effect that when you go down, the density of the fluid increases a little bit, but mostly your fluid is incompressible, so it doesn't really increase the density. But we will say that the buoyant force actually remains the same. All right. I'm going to work through this next series of questions. So if I have, here I have a container. It has a little spigot that comes out the side here. That spigot is a distance h from the top of the fluid and a distance ¼ from the bottom of the container. And first of all, I want to know if h is 20 meters, then the pressure at C is what? Is it 1, 2, 3, or 4 atmospheres? Any ideas on what that might be? The pressure at point C? The pressure at point C is just at the opening of this spigot. It's going to be 1 atmosphere. Yeah, so the pressure is 1 atmosphere. You can think about this in a couple different ways. First of all, at this point C, there is no fluid above it other than the atmospheric pressure. So that's probably the easiest way to think about it, is that there is no fluid. Now, if I was over here, you roughly get 1 atmosphere for every 10 meters. So if I was over there, it'd be about 2 atmospheres. Right? So are any of y'all divers? Any scuba divers? So scuba divers know that for every 33 feet, you get an increase in pressure of 1 atmosphere, 33 feet of water. If the container is filled with water and h is 20 meters, then the velocity of water at C is which of these? This was a little tricky, actually. If you imagine a water molecule, say up here, and it goes, I have this little water molecule, it has a certain amount of potential energy, right, mgh. When it comes out down here, all of that potential energy is going to be converted into kinetic energy. So I would have mgh equals 1/2 mv squared. I've seen a number of these types of problems, so it's probably useful for you to just remember this, that my water molecule at the top, if I imagine that it falls all the way down to the spigot and then comes out, it's going to have a velocity that has an energy equivalent to the gravitational potential energy that it had before. That is given by mgh equals 1/2 mv squared. So this simple conservation of energy problem, if I want to know the velocity, I just say it's the root of 2gh. Solving that for v, that is the root of 2 times 10 meters per second squared times h, which was 20. What's that? 20 times 20, or the root of 20 times 20 is just 20 meters per second. All right. Would y'all have known how to do that right off? You wouldn't have approached it from that way at all, would you? I wouldn't have either, actually. But I think it's probably useful for you to just see this type of problem, because I've seen it on a number of different practice tests. But again, you know, on the MCAT, who knows what topic you're going to get? It could be any one of the topics. Am I right about that? Yeah. Anthony?
I guess I'm kind of confused why you use the 20 meters for the height and not the 1/4 of the height. That's good.
Oh, because imagine that if I have a stone or whatever, and I drop it from this point, it has a certain gravitational potential energy, and then as it falls, we're calling this h equals 0. Down at this point, the gravitational potential energy is 0, and it only has kinetic energy, 1/2 mv squared. So this whole ⁄4h is irrelevant, because we're setting our h equals 0 to be right here. Does that answer your question? Yeah, don't think of it as a fluid question. Think of it as a energy question. Conservation of energy. All right. Okay, so now I want to know what's going to happen with h as or what's going to happen to the velocity as h decreases. So as this level of water drops, what's going to happen to h? Is the velocity going to increase or decrease as the h drops, as the height of the fluid drops? So as this can drains out, what's going to happen to the fluid, or the velocity at that spigot? Is it going to increase or decrease? It's going to what? You try again? It's going to decrease. Very good. Yeah, so because if you imagine this energy problem, your water molecule, the height of your water molecule is getting lower and lower, and so it gets less and less potential energy. And so as h goes down, as the water level drops, that is, as h decreases, the velocity is also going to decrease. Because remember, we had this mgh equals 1/2 mv squared. And so as h goes down, v also goes down. All right. So we can also show that by this relationship that we have a relationship between h and v squared. So if I solve this, I get h equals v squared over 2g. All right. So that means that I have h equals some constant, which is 1 over 2g, times v squared. Which of these graphs represents an h versus v squared? Why don't we try this as a clicker? Which of these graphs represents h versus v squared when I plot h versus v, rather? This is a quadratic function. Which one is it? I'll stop at 45. All right, let's see. The answer is C. Is that right? Oh no, not C. It's not C. Did I put C? No, it's B. Excuse me. Yeah, guys, see, that's a linear function, right? If I plot h versus v, that would be this graph right here would represent h equal to some constant, whatever that constant is, times v. But instead, I have an h versus v squared function. That's a quadratic function, which is going to be b. All right? You have a question for me? B and D. So, we've already said that if h goes down, v also goes down, right? So here, as I move down this graph, h goes down. See, as I move, is that right? Yeah. So this is a direct proportionality, and this is an inverse proportionality. See, this would show that if h goes up, v goes down.
I was kind of looking at the slope, and the slope is decreasing, and h is decreasing, v is decreasing, so that's not.
Mm-hmm. These are hard questions. Yeah, Michaela?
Why doesn't it follow that as you get lower, the kinetic energy is increasing? So you would think the velocity would increase with the kinetic energy.
As you get lower, what do you mean?
Like from that h equals 20 to that h equals
Mm-hmm.
0, wouldn't the kinetic energy be increasing?
The kinetic energy of...
Like you're using the
Oh, I see. So you're saying that the level of the fluid is dropping. So at the top of the fluid, since this level is dropping, then actually molecules up here have a certain amount of kinetic energy. I think that kinetic energy is so much smaller because the velocity of it dropping at the top is so much smaller than the velocity of it coming out the spigot. So yeah, technically you're right that it does have some kinetic energy at the top, but it's negligible compared to the kinetic energy at the bottom.
And that's what I was saying. I was thinking if it's increasing as you get lower, wouldn't the velocity increase as you get lower with the kinetic energy?
I'm not sure, Michaela.
I think she's thinking about it presently as the process is going on, but what we're talking about is that like whether it's set at a certain age at the beginning initially, or if it's the age is shorter. Initially.
Right.
That's
Yeah.
what the question's asked.
Mm-hmm. You understand what he's saying? That we're imagining it, actually I've sort of been talking about it in this way, as time progresses. But instead, it's looking at how does h compare to v. Like if I drop my level of h, how does that affect the velocity coming out? And if I drop my level of h, that's going to decrease the velocity that it comes out. All right, so like having a whole bunch of different containers with different levels of h, not a container that progresses with time. That's a good way of describing it. Okay, Heather?
Okay, what she was talking about, I was looking at the slope also, but the slope is the acceleration. Is that right?
The slope, no, this is, no,
So
this is
what-
different.
What is the slope? Because I was looking at the slope thinking,
Well,
the slope is negative, so then velocity would be negative, but obviously that's not right.
yeah. This isn't a displacement versus time graph or velocity versus time graph. If it were, you would look at it at the slope in that way. All right. Is that satisfactorily answer your question?
Yeah.
Okay. All right, let's move on. I don't want to get bogged down on any one topic. But these are good questions. These are hard questions. MCAT's a hard test, I think. Don't y'all think so? But y'all are going to do so well on it. All right, let's move on to 594. So try this one. Yeah. Oh, yeah, of course. And then we will move on to a couple different topics. This question is similar to, or is dealing with the flow, that your flow rate has to always be the same. If you remember from 102, it's also the junction rule, basically, an application of the junction rule. No, I skipped that. All right, about 5 more seconds. We have 18 people now, is that right? All right, good. I think we have 18. 2, 5, 9, 12, 18, yeah. B, that must be right. All right, so let's see, you can just look at the flow rate coming in. So here you have 8. Here you lose 2, so you have 6. Here you lose 4, so you have 2, and here you gain 3, so you have 5. That's how y'all are looking at it? All right, good. B is the right answer. Okay, we'll do some more questions, but first I want to do one final topic in this chapter, and that was on tensile stress and strain. We covered this in 101, although we just did it in one dimension. Remember the Young's modulus by chance? If you pull something, if you apply a stress to something, then it will deform the object. So, where are my notes? All right. Stress, whenever we talk about pressure, or whenever we talk about stress, we're always referring to the force per unit area, the force per area. So this is very similar to pressure, but we're referring this now in terms of solids. So whenever we talk about fluids, we'll call it pressure, but when we're talking about solids, we'll call it stress. Stress always leads to a strain. So stress is always proportional to the strain. The strain is just the deformation, and you can measure the deformation in a couple different ways. We'll look at it in 1 dimension, 2 dimensions, and in 3 dimensions. In 101, we just did it in 1 dimension, but the 2 and 3 dimensions are very similar. All right. Basically, it says that the force per unit area is equal to some constant. In linear terms, we call this y for Young's modulus, delta L over L. or we sometimes call this L naught. So if I apply a certain stress, it causes a certain object of a length to increase by a delta L. So if this is my bar or whatever, it is a length delta L. I apply a force to it, and that makes it get bigger. All right. You also have to know the area because you're actually concerned with the force per unit area. Can y'all see over here? That's an L naught, yes. So L naught is the original length. I'm sorry, the initial length. All right, so that's in one dimension. This is called the Young's modulus. But you also have it in 2 dimensions as well. In 2 dimensions, it's called strain. I mean, not strain, shear. Can I go down from here? If you imagine it's like a book, there's a picture in your book actually. But if you take a book like this, and if you apply a force to it, if you have a book like this, you apply a force to it, notice how it's deformed, how it sort of, the top goes away from the bottom. You see that? Okay, so that's the deformation, the shear, and we describe that with the shear modulus. And you're going to force over area. This is going to be, like if I have this book, it'll be the top of the area. We'll work a problem in just a second. Ooh, the shear modulus, I forget what it's called. It's called S in your book, but I think it uses it different elsewhere. The shear modulus, and then that's going to be... hold on, I'm sorry. Sorry, I forgot. Let me look at my notes real quick. What's that? Oh, no. No, it's a little bit different. I'm looking at something different here. So the shear modulus is delta x over h. I'll show you a problem in just a second. We'll apply it. And then you'll also have a bulk modulus. I haven't seen any problems actually associated with this, but I'm just going to tell you sort of about it in words. Bulk modulus says if you have an object, like a 3-dimensional object, and you apply a certain pressure to it, that object will get smaller. And the bulk modulus will describe how much it gets smaller. I think it's something like this, that the force per unit area is equal to the bulk modulus, which is a beta, times delta V over V, where this is our volume, our change in volume. So if I have a certain sphere, oh, it's like a smiley face, but if I have a sphere and I apply a force per unit area to it, then that sphere will actually get smaller. Okay? Let's work through some problems there. In the handout that I gave you, let's look at number 617. 617. I'll pull it up. .617 here refers to this table right here, and it says, according to the table, which of the following can withstand the greatest amount of stress without breaking? So remember, stress is that force per unit area. Glass, the bone, concrete, or aluminum with those given dimensions, lengths and radii. If you finish this, we're going to go on to 626 and 627. 626 and 627. But right now, 617. Just this problem. All right, about 5-10 more seconds. I'll stop at 2:05. 2:05. Okay, you're all overthinking this. The answer is B. The reason it's B is it has the ultimate strength given. Now, and then it's showing that they all have the same amount of stress. Now remember, stress is not a force. It's a force per unit area. Now it might be that, what was the most common answer? See, C. It might be that the concrete cylinder might be able to withstand a greater force, but not the greatest stress, because the stress is ultimately given just by this ultimate strength. So you just want to find the one with the greater ultimate strength. Y'all follow what I'm saying? That it's really stress that you're concerned with. So the dimensions of the object doesn't matter about the dimensions of the object. All right? So of these, the glass, the bone, the concrete, and the aluminum, the bone has the bigger ultimate strength, which is 1 million newtons per square meter.
It's twice as thick.
Is it twice as thick? Yeah. The what is?
It's twice as thick as iron.
Right. But the dimensions are irrelevant because it's asking for stress. It's telling that you have the same stress, and stress is force per unit area. So the dimensions don't play into this at all. All right, let's look at number 626, and then we'll do 627, then we're going to move on to waves and sound. All right, 626. We're doing 626 right now, 626. Remember what apparent weight is. Apparent weight is the actual weight minus the buoyant force. So like you feel lighter in a swimming pool, right? Because your apparent weight is less than your actual weight. All right, I'll stop in about 10 seconds. 115, 115. 5 seconds. Okay, so what happens as you go deeper? What happens to this object? It does what? The pressure gets bigger, right? So your stress gets bigger, and so it gets smaller. What happens to the buoyant force if the volume of the object gets smaller? What happens to the buoyant force? It doesn't stay the same. It decreases, right? I know we were talking about earlier that as you go deeper, the buoyant force remains the same, but here we're considering that this, what is it, a lead ball, that it has a certain bulk modulus, 7.7. Actually a pretty small bulk modulus, that if you apply a stress to it, it's going to make a big change in the volume. All right. So as it goes deeper, the volume of that sphere is going to get smaller and smaller because of the pressure pushing in on it. And that's going to cause the buoyant force to decrease. And if the buoyant force decreases, what happens to the apparent weight? It does what? It increases, right. If my buoyant force decreases, then my apparent weight increases. So that was B. Okay. I have this object, right? It's a ball, and it's in water or whatever. As it goes down, that object, because of the pressure of the water, it gets smaller. So as it descends, it gets smaller. Like a submarine, right? Submarine, you go down to the crush depth or whatever they call it, it'll get smaller because of the pressure. And if it gets smaller, that means that the buoyant force, remember buoyant force, rho pg, the density of the fluid, volume of the object times g. If that volume gets smaller, my buoyant force becomes less.
As you know, the lead's all the way to the bottom.
It doesn't matter if it's all the way to the bottom. Good. Just like it just, as my volume gets smaller, my buoyant force gets smaller. And if my buoyant force gets smaller, the inherent weight gets smaller.
You're so confused, because like on the first page, the problems of the fluid submerged solid sinks deeper in the water, and so the buoyant force remains the same. As it submerges.
Yeah, but there we weren't dealing with this whole bulk modulus. So there we are assuming that the volume remains constant. I understand what you're saying. I know it's also on the first page, but really, like in the book, it was separated by many, many pages.
So how does the bulk modulus come into play?
The bulk modulus describes how the object changes when you apply a pressure to it.
So that's a high bulk modulus. That means it'll get even smaller, or it has more.
If it has a low bulk modulus like lead does, that means that it changes shape really easily. Right, so it will get smaller. Right, lead is more malleable than these other things like copper or steel. All right, does that make a little bit of sense? A little bit, at least. Okay. All right, let's do this last problem, then we'll take a little break. So a force is applied to the top of a copper block as shown. If the bottom of the block is fixed to the ground, how far to the left will the top shift? Right? Remind you that our shear modulus is F over A times our shear modulus times delta X over H. Can I just work through it here? Is that okay? All right, so my force here is 10 to the 6 newtons. My area is going to be 4 meters squared. The area involved here is this area. All right, and this area is 1 meter times 4 meters. So 10 to the 6 newtons over 4 square meters. And that's going to equal to my shear modulus, which, let's see, this is copper. And so my shear modulus is 40. Oh, no, it's not just 40. It's 40 giganewtons per square meter. So it's actually 40 times 10 to the 9th newtons per square meter. If you look up in the sentence above, it says giganewtons. And then delta X is what we want to know. How far to the left will it shift? So we want to know, like if I'm doing my book, how far does the top of the book go over? Delta X over H, which is just the height, which is going to be 2 meters. And then you solve this for delta X. If you solve it for delta X, you find that delta X is 1.25 times 10 to the minus 5. All right. So as I said, we did Young's modulus in class, but you can see some bulk modulus, or some shear modulus as well. I've seen several problems on some of the practice tests. All right. The tricky part is just knowing what all these various variables refer to. And I've actually seen in some problems where they usually give you this shear modulus equation. All right. Let's take a little break. We'll come back here at, is a 5-minute break okay? Is that enough for y'all? Okay, we'll come back here at 2 o'clock. All right? Yeah, 2 o'clock. We'll start waves next.
Wait. Yes. I watched it. Oh my God. Like, he didn't stick me still.
Oh man. How was the cheerleading competition?
The tryout.
How was the tryout?
It was awkward because they
They weren't very good.
no, they were a really good team. They told the girls who did not make it while we were there. Yeah. Like while I was there, it was like we had to go like while they was like tallying the scores to see who made the team. They made us go talk to the girls.
Oh really?
Yeah.
Was it high school or college?
It's weird. It was high school.
Yeah.
It's kind of awkward, but hey, got to pay for it.
Right. Alright guys, shall we get started again? Okay, so with these, they all have this form, Young's modulus, they all have the form of stress, F over A, is equal to some modulus, whether it be the Young's modulus, the shear modulus, or the bulk modulus. And really the only difference is this deformation, or the strain. So for Young's modulus, it deals with just a change in length. For the shear modulus, it deals with this shifting over of the top portion from the bottom, this delta x over the height of the book. So this is like the book, where the height would be this, and then delta x would be the amount that it shifts over. And then for the bulk modulus, this deals with 3 dimensions. So it goes from one size to another size. So it has a change in volume. But they all have the same form for tensile stress and strain. All right, we're going to move on to chapter 7. Now, as I said, the test next week will be chapters 1 through 6. And on Monday, I'll send y'all some practice problems, and I'll put some screencasts online so y'all can sort of get a feel for what the exam will be like. But it'll be like a lot of the questions that we've been working in class. Okay, so I would look back over those. But I know that you've had just an onslaught of questions. Are there any questions right now? Evan, you had a question? Okay. We're going to look at waves. We don't typically deal with waves in Physics 101. We do it in the 200 level, but we don't typically get to it in 101. So some of this might be new to you, but I expect that you did this in chemistry as well, right? Y'all deal with waves in chemistry? Yeah, okay. So just sort of basic principles about waves. I'll go through them quickly, and then I have some questions for y'all to work through. And then we'll get to sound as well, which you might not have ever seen before. The sound, you often don't get to it in a physics course for whatever reason. It's just sort of a side topic. We have 2 different types of waves, transverse and longitudinal waves. Transverse waves are like waves on a lake. These are transverse. And then longitudinal waves are like compressional waves. So like I have a compression here, and then I have a rarefication. I have a compression, a rarefication. You understand, like a slinky. Like if I were to put a wave in a slinky, you would have places where it's compressed and then places where it's rarefied. So this is called a longitudinal wave. Yeah, Rory?
I always thought like waves are like a sound waves.
It is a sound wave, yeah.
It's like
Huge what?
parentheses looking sunlight like on.
Okay.
My
Yeah.
job. basketball.
Yeah, draw it on the wall, please. No, yeah, I understand what you mean, like this.
Right.
Yeah, that's a good way of thinking about it. Where these represent the compressions and these represent the rarefactions. Where you have high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. But you can have longitudinal waves that are mechanical as well, like in a spring, right? So these are all longitudinal waves, and we'll deal with that when we get to sound. But you have similar things with longitudinal and transverse waves that describe them. You have the wavelength. The wavelength is the distance from peak to peak. You have the period, or rather you have the frequency. The frequency is equal to 1 over the period, and the period, t, is the time for the wave to travel one wavelength. And these two are related, these three things, that is the frequency, the wavelength, and the velocity in this way. The velocity is equal to lambda times the frequency. The frequency, by the way, is measured in hertz, Hz, hertz for H-E-R-T-Z. You've probably seen this on electrical devices because they have a certain frequency because our electrical signals are actually alternating, and so they have a frequency. A hertz is equal to 1 over a second, and so if you look at the units for this, in this equation right here, lambda is in meters, frequency is in 1 over second, so that gives you units of meters per second. So if you ever forget this equation, just think about the units. It's going to be lambda times the frequency. We'll give you the velocity. Your book gives the function for a wave. X is equal to a sine of omega t plus the phase angle. I'm not going to spend too much time on it because I haven't seen any practice problems that dealt with this. So just sort of give you a brief primer on this. A is the amplitude. Yeah, if you were in 201, we did this last semester. You remember? I think Andrew, you're the only one I think in 201. A is the amplitude. If I have a wave like this, the amplitude is this distance. That's the amplitude. That will come up a little bit later in a practice question. Omega is something we call the angular frequency. It's related to the frequency. Omega is equal to 2 pi times the frequency. Right? Omega is equal to 2 pi times the frequency. And phi is the phase shift. I'm not going to get into the phase shift, but I just want to show you roughly what phi describes. But I haven't seen it in any practice problems, so I'm just going to skip it here. If I have two waves that are shifted by a certain amount, that just means that they're shifted with respect to one another. And that phase shift describes how they're shifted with respect to one another. All right? You might have seen this in one of your math classes before. Often math classes will deal with this. So, you can have different types of interference. Can I go down from here? You can have constructive interference. Constructive interference occurs when I have two waves where the peaks line up with the peaks. Like this. If I were to add these two waves together, I'd get waves with bigger peaks and bigger troughs. They would add up like that. Or I can also have destructive interference. And destructive interference occurs when I have waves where the peaks and the troughs don't line up. Or the peaks don't line up with the peaks. What do I get if I add these two waves together? Right, you just get a straight line. You can see this actually out on the water. If you notice, you'll see two waves start to come together, and you can watch for where the waves come together. They'll make either bigger waves, or they'll make deeper waves, or sometimes you'll just get flat spots where they come together. It's kind of cool to sit and watch the waves come together. So y'all can try that. We see this in light as well, and we'll revisit this when we get to light for diffraction, interference and diffraction. All right. Let's try a couple of questions. Just sort of basic principles. Let's look at number 637. That's in the handout that I gave you, number 637. And then we'll do some practice tests too. Number 637. There it is. 637. If you finish 637, go ahead and do 639. All right, we're going to skip 638. But right now, I'm up for 637, and then you can go on to 639. All right? About 10 more seconds. Okay, I'm going to stop at 220. 220. Okay, A is right. You have some extraneous information here. Really, all you need to know is what? Just the frequency, right? Because I'm asking how much time is required for a single wave to pass by an observer. I'm asking for the period. That's just going to be 1 over the frequency. That's 1 over 200, which is 0.005, all right? 1 over 100, right, is 0.01, so half of that would be 0.005. All right? Let's do number 639. These are just sort of basic principles for waves. If you finish 639, go on to the next one, 645. Be thinking about that. Right now, 639. I'll stop at 55. It's 10 more seconds. A is right. Alright guys, don't forget we can find our velocity. It's just going to be the wavelength times the frequency. Okay, wavelength times the frequency. The wavelength, I'm looking for the wavelength. So it's going to be the velocity over the frequency. The velocity is 10 over 200. That's 1 over 20, which is 0.05. 639? Yeah, it's 0.05. That's what I marked, right? 0.05. A. Okay? Y'all okay with that? Calculate various principles or various properties of a wave. You're excited about it? The wavelength? No. Okay. Which of these determines the velocity of a wave? I'm just going to tell you the answer here. Now, it is true that the velocity is equal to the wavelength times the frequency, right? So you would think, well, maybe it's the frequency or maybe it's the wavelength. But both of those answers are given there, right? So which is it? It's neither, right. So neither actually gives the velocity. The velocity is determined by the, not the amplitude, the medium, right. So the velocity is given by the medium. If this helps you to remember it, you remember when we were doing light, when we were doing refraction, when light would enter a different medium, it would actually change speeds. The same is true for sound and other waves, that when light enters a different medium, it will change speed. You can see this too. Do you see that on the water? No, maybe not so much. If your water actually changes temperature, it'll change, the waves will change a bit, but you probably can't really observe that. So the velocity is not dependent upon the frequency or the wavelength. Even though you have this expression, the velocity of a wave is governed only by the medium. Is that clear? Only by the medium. All right, let's look at number 646. What's the wavelength of this wave? And then go ahead and look at and tell me what is the amplitude of that wave. We've only looked at very regular occurring waves, but you can have recurring waves that are not as simple as what we've seen. You want to find the pattern. All right, stop at 135. Sorry, or 132. Okay, very good. Is C? You want to look for C. You want to look for recurring patterns. Right, it's like kindergarten, right? You look for patterns in kindergarten, and so here you want to look for a pattern. Notice that I have this wave, and it begins to repeat right here. Notice I have this peak, here, 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 and here, roughly. So this wave repeats in this pattern, so my wavelength is 4 meters, because that's the distance over which it repeats. What is the amplitude of this wave? So looking at 649, the amplitude is 4 meters. The wavelength is 4. What is the amplitude of this wave? Stop at 1 minute. 1 minute. 5 seconds. Okay, C is right. Remember when we were drawing our sine wave, when it looked like that, our amplitude was half the distance from peak to peak. So it is half of this distance. This is 2a, and so our amplitude is that. So you can measure the distance from the lowest peak to the highest peak and take half of that. But in this figure, it already shows you the sort of the origin. And so the amplitude is just this distance. See, a number of you put 1 centimeter. Why is that? Why did you put 1 centimeter? Oh, you took the average. No, don't do that. It's going to be to the highest peak. From the lowest peak to the highest peak. A lot of you put 1. Was that also what you were thinking? Sort of the average? Okay. No, you want to go from the lowest to the highest and then take half of that. Or, as the line is already drawn sort of down the middle, you can just go from that origin up to the highest peak or to the lowest peak. The average, huh? All right, but C is the right answer. Let's see. And then do this one, then we'll move on to sound. We've already said this. What is sound wave? Longitudinal, transverse, gravity, or an electromagnetic wave? That's 659. Stop at 40. Very good. So this is a longitudinal wave. We also call it a what? You may remember? A compressional wave, right? So that sound is actually a high pressure and a low pressure, a high pressure and a low pressure, and that's actually what impinges upon your ear. Like when you go to rock concerts or whatever, and what damages your ear. But y'all don't go to rock concerts, do you? No. Good. Did y'all know that I used to play in a band? Did I ever tell y'all this? I did. I mean, I play in a band now, but that's like a church band. But I used to play in like a heavy metal band. We're a lot more subdued than the heavy metal band that I used to play in. Though we went to church the other day, and I had jeans and like a t-shirt on, and my wife was all dressed up, and my little girl said, "It's okay, Daddy, you're in the band." So it's like I'm the cool dad now, because I'm in a band. All right, that's a pretty dorky band, all in all. All right, so where were we? All right, so let's look at sound. As I said, I'll make some practice problems. If I made some practice problems, would y'all use them?
Yes.
Okay, I'll make those on Monday. I'll get those up. So I'm sorry I don't have them for the weekend, but it's just been kind of crazy. So I'll make practice problems to help y'all prepare for the exam coming up. And guys, don't forget, we have an exam next Friday, but then the following Friday we're going to have another exam. It'll be slightly less material because it'll just be slightly less material. It'll probably be 7, 8, 9, and 10 or so. Yeah, Alex?
Stuff we're doing right now is chapter 7.
Right, this is chapter 7, which is not on the exam, but it'll be on the next exam.
But everything we covered before.
Yeah, we were sort of just still reviewing that stuff. I just wanted to spend a little more time on it. All right? This about the right pace for y'all? Too slow? Too fast? Too tired. Yeah, I understand. All right. Let's see, where are we? Interference. Um, we're going to look at harmonics and resonances, standing waves. When I was a kid, I went to a boarding school, a high school, and we had this big column. It was a stairwell. Y'all can do this if you live in a dorm. You can do this. All you need is like a frequency generator. It's just basically a power supply, and you can hook it up to a speaker, and it just generates a tone of a particular frequency. Or you could just go online and you can like type in a frequency of whatever, and you can download it to your iPod and put it on speakers. Anyway, we were able to find the harmonic frequency of this big column. And basically, you know what a harmonic is? Like when you get this standing wave within a tube or whatever, like in an organ or like in a musical instrument, you produce these harmonics, these standing waves within it. If I were to look at a tube, like a closed tube on either end, the harmonic, I'd have this wave that would begin and end at the ends of the tube, and you would get this sort of kind of sound. Y'all know what I'm talking about? Yeah, but in our high school we did this, me and a couple of friends, and we were able to get the whole building just sort of vibrated because we turned up the speaker and it was vibrating at the harmonic frequency of this stairwell, and it was just woo, and the windows started shaking. It was really kind of cool, actually. So you can determine what are these frequencies. This only occurs at particular frequencies and particular lengths of the tube. So let's see, this is on page 56 if you're following along in your book. The frequency, the harmonic frequency of these waves for a given tube are given by N. This is the velocity of the wave. This is the node. I think it's called the node. It's just an index. So this is just a number, 1, 2, 3, and on, because you can have multiple waves that will fill that space, divided by 2 times the length of the tube, where this is the length of the tube. All right, so our frequencies, where N here is equal to 1, 2, 3. This gives the frequency of these harmonic resonances, right? The resonant frequency for a tube of a given length, right? Where V is the velocity of the wave and L is the length of the tube. Now you can find another expression for this, because I know that V is equal to F times lambda, and so you can substitute this into that, and you can find that that L, the length of the tube, is equal to N times lambda over 2. All right, that's just plugging in this V equal F lambda. I'll let you do that on your own if you like. And you get the same expression. So these are similar expressions that describe the harmonic frequency or the harmonic resonance frequency of a tube with closed ends. All right. Also, regarding simple harmonic oscillations, we usually talk about Hooke's law with regards to this. Can I just go to the next page? Is that okay? We'll work some problems with this in just a few minutes, okay? I just want to go over sort of the basics. All right, so Hooke's law, we had this in Physics 101. This describes the force to a spring. It's minus kx. So if I have a spring, I have a mass on it. The spring applies a certain force, and the magnitude of that force is dependent upon how far you stretch it. So the farther you stretch it, the more the force is going to be. All right. If I have a spring that is oscillating, so this mass is oscillating back and forth, going back and forth, like that. I can describe it in terms of period and amplitude and all that jazz that we do with simple harmonic motion, like the waves going up and down. And the period of this is equal to 2 pi square root of m over k. We also had this in Physics 101, I think. Did we cover this in 101? Maybe not, but in 201 we did, yeah.
Integral stuff?
No. It's my understanding there's no calculus. Is that true on the MCAT? No, I don't think there is.
PCAT has to.
Oh, really? Are you taking the PCAT?
Yes.
No. Okay.
What is it?
The pharmacy. So anyway, the period of that is 2 pi square root of m over k. I think we'll see that in a practice problem in just a bit. We have similar things. Oh, and then you can also describe the amplitude. So if I have a original position, x equals 0, this mass will go back and forth, oscillating back and forth. We did a problem like this in the lab in Physics 103. Remember the mass oscillating up and down on the spring? You had to measure its period. We can also find the amplitude. The amplitude is this distance, measuring from the origin, the center point, out to one of the extremities. We can also have a pendulum. And a pendulum, if I have a pendulum here, I will get simple harmonic oscillation when theta is really, really small. Get simple harmonic motion. That means this motion that's described by this sine wave when theta is really small. We can describe the period of this. T is going to equal 2 pi square root of L over G. That gives the period of the motion. Notice it's only dependent upon the length of the string and the acceleration due to gravity. We can also describe the frequency of this. The frequency, again, is going to be 1 over the period. All right, let's work some basic problems, and then we'll go into Chapter 8 about sound. Chapter 7 and 8 are both pretty short. Gosh, we're going to get to electric stuff today, too. Good. All right. We might actually finish through Chapter 12 in this class. We'll see. Let's do a few problems. We'll do the handout that I gave you. Okay. I'm going to just show you here number 662 because this wasn't actually covered in the book. But when I have a wave here that is sent down a taut rope, have you ever done this? Like where you take a rope and you just shake it like this and you get a wave that goes down the rope? The velocity of that wave is equal to the root of the tension over mu, where mu is the mass per unit length. Or m over L. All right. So if I have a greater tension, my wave will go faster down the rope. And if I have a lighter rope, that is where mu is small, then I will have a greater velocity on the rope. So which of these will change the velocity of the wave? Changing the frequency of the wave, the length of the rope, the tension in the rope, or the amplitude of the wave? Right. So the tension is the only thing of these things that will affect the velocity of the wave. You could also change the mass of the rope or the string or whatever. If you make this smaller, as you might expect, on a smaller rope, that wave will travel faster. Would you expect that? Yeah, a big old heavy rope, it's going to move very slowly. But a very thin rope, it'll move more quickly. Oh, this isn't this is a mass per unit length. All right. It's not really correct for me to put m over L. What is just the mass per unit length. So for every measurement in length, how massive is the rope? Is that clear, Alex? The tension in the rope and the weight of the rope. That's right. But the weight of the rope isn't here. Right. The mass of the rope isn't an option. Okay. Let's see. Do I have questions about this? Yeah. Let's move on to the next page, and then we'll come back to this. All right, so number 680, which of these waves is in phase? Which of these waves is in phase? X, Y, and Z, or both X and Y? All right, I'm going to stop at 110. 110. It's 5 more seconds. Okay, A is the right answer. Very good. Remember, if they're in phase, that means that you're going to get total constructive interference. That means they're going to add up, so your peaks line up with peaks, and your troughs line up with troughs. Which of the pair of waves will experience only destructive interference? So number 681, which of these waves will experience only destructive interference? Number 681, X, Y, or Z? Let me finish that, go on to 682. I'll stop in just a few seconds. Looks like everybody's in. Very good. B is right. That's total destructive interference. And when those add up, if they have equal amplitudes, here they don't, but if they had equal amplitudes, you just get a straight line. Here, actually, you're just going to get a very low amplitude wave. So as they add up, you still have a little bit of residual wave left because the solid line, it has a bigger amplitude than the dotted line. Follow me on that? All right, and then number 682, which of these will experience only constructive interference? Have we had that question? Oh no, it's a little bit different. All right, go ahead and click in. Yeah, Mary. That's right. I'm sorry. I'm not sure if I said that explicitly. Yeah, I'm sorry. In phase means that you have total constructive interference. Out of phase means that you have total destructive interference. So in phase, they're lined up. Out of phase, they're not lined up. Yeah. All right, so a few more seconds. I'll stop at 40. That's right. If it's constructive, it has to be in phase. All right, A is right. Same as for number 680. Is everybody clear on what that means? Constructive, destructive, phase, in phase, out of phase? All right. We'll come back to 694 when we talk about beats. And let's try 700. We haven't talked about this explicitly, but I think you probably know it. This work okay with the questions like this? Yeah. If you finish this, go on to 702. Just a few more seconds. I'll stop at 45. All right, D is right. Very good. So your frequency gives the pitch of the sound. So like if you have a really high pitched sound, it'll have a high frequency. A low pitched sound will have a low pitch frequency. Low frequency. We like to do this in our house. Have you ever done this? High, low, high, low, high, low. Oh wait, no, we do it differently. No, we don't do it that way. See, it's very hard to do. We go high, low, high, low. Can y'all do that? Try it. See? No. Whoa. 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 High. Right. Whoa. High. Whoa. High. Try it. It's hard. It's like rubbing your belly and patting your head at the same time. It's very difficult to do. All right? Y'all can do that outside of class. Okay. Let's try number 702. This gets back to our resonance frequencies. If you recall, I'll just remind you what the equations were. We had the frequency, thus the resonant frequency is NV over 2L. But we can also write this as L is equal to N lambda over 2. The length of the first harmonic would relate to the wavelength. So the first harmonic, if this was our string like this, our first harmonic would look like that. I'd have a wave set up on the string that would look like that. So the length of the first harmonic would be the wavelength. All right, so a few more seconds. I'll stop at 135. 135. Okay, A and B. So the length. Yeah, the answer is no. It's not A. It's C. No, it's D. Yes, D. D is right. So the length is equal to n times lambda over 2. Here, n is going to equal 1 because I'm looking at the first harmonic. You can have multiple harmonics. Like I can have multiple standing waves here. Like that would be the second harmonic, and then I can have the third harmonic and the fourth harmonic. Mary? Right. The number of nodes that you have. So here, my length is. I want to know the length of the first harmonic. So that length is going to be the wavelength. What is the length of the first harmonic? So I'm solving now for lambda. N is equal to 1. So L is the length of the string. That's 36 is equal to lambda over 2. And lambda then is equal to 36 times 2, which is 72 centimeters. All right, I'll try to pull y'all some more questions about this. It's really just sort of reading the questions and knowing what the values are. Yeah. Oh, because it's the first harmonic, as opposed to the second harmonic where n would be 2. All right, I'll pull some more questions for y'all on this. Let's try number 706. This is similar. Here you first have to find this harmonic equation, n lambda over 2, to find the wavelength, lambda. And then, remember this relationship, where the velocity is equal to the lambda times the frequency. So there's 2 steps in this. About 15 more seconds, 10 or 15 seconds. See what we need. $2:35, I'll stop. I think that's everybody. All right, so A is the right, is A the right answer? A, it is the right answer. Very good. Just sort of got to know this, how to find those frequencies. All right, so you'll sort of need to memorize this relationship, and then of course you need to know this as well. So if I find my wavelength, I find that my wavelength for the first harmonic is twice the length of the string, so that's going to be 60 centimeters. The wavelength of the first harmonic is twice the length of the string. All right, n equals 1. This is my wavelength. This is the length of the string, so the wavelength is twice the length of the string for the first harmonic. Y'all with me on that? Y'all with me? Yeah, so you can see that, like if I imagine that I have this string, remember the first harmonic looks like this, where my wave just sort of goes back and forth. Yeah, I'm sorry, that's the first harmonic. I drew the second harmonic before. I'm sorry. See this if I have a wave on a string like this, then the first harmonic looks like that. If I represent the wave, am I confusing y'all? This is confusing you. I understand. I drew it improperly before. I'm sorry. Let me try to rectify that. I have a string right here. It's fixed on both ends, and then I have a wave that is standing on it. All right. And that wave goes back and forth like this. But notice that I've only drawn half the wave, right? So the wavelength of the first harmonic is actually twice the length of the string, because I've only drawn half a wavelength here, and so the first harmonic is twice the length of the string. The first harmonic is twice the length of the string. Y'all with me on that? That comes about in this expression, L is equal to n lambda over 2. If n is equal to 1, then the wavelength is twice the length of the string for the first harmonic. On the second harmonic, it'll look like this. I have the same string. In the second harmonic, the wavelength is equal to the length of the string. Okay? I'm sorry for getting that wrong before. Is that clear now? Sort of? That comes about in this expression, which you should probably just know. I've seen these come up a number of times in the practice test, so they're resonance frequencies. Once you get the wavelength, you say V is equal to the frequency times the wavelength, and we're looking for the frequency here, so that's just going to be the velocity, which is given, 264, divided by the wavelength, which is 0.6 meters, and that has to be 440. All right. You could just think of it as 260 divided by a half, which would be 520 roughly, but it's actually not quite a half, so it's something less than 520. All right. Let's look at beats now, and then we'll come on to some of these other questions. Beats are pretty simple, especially if you play. Do any of y'all play the guitar? You like play the guitar? You know how you tune a guitar where you play one string at one note, and then you play another string at another note? And if those two strings aren't playing the same frequency, what do you hear? You ever tune a guitar? Okay, if you play one string at one frequency and another string that should be at the same frequency, but they're not at the same frequency, you hear this wah, 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 wah. Yeah? You can do this with a piano too. That's how they tune pianos. They take a tuning fork, dung, and then they play the note. And if the two aren't the same frequency, you'll hear this wah, 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 wah. You've heard that before? Those are called beats. And beats come about because you're putting these two waves together, and they have different frequencies. The nice thing about beats is the number of beats is proportional to the difference in the frequency. Pull up my note page. So the number of beats is equal to the absolute value of the difference in the frequencies, F1 minus F2. All right, just what is the difference in the frequency? So if I had a sound with a frequency of 50 hertz, 50 cycles per second, and then I had another with a very close frequency, 52 hertz, then I would hear a beat, I'd hear 2 beats. I think it's actually 2 beats per second. Let me double check that. Yeah, it's the number of beats per second. So I have these two very close frequencies, and so I would hear 2 beats per second when I bring them together. 2 beats per second when I bring them together. It's a really nice way to bring things into tune, to bring things into the same frequency. So let's look at a couple of things. Let's look at number 694. On number 694, I have 2 notes that are coming together. Now these aren't just simple notes. They have lots of sort of overtones where they have many different frequencies that are adding together. But here we see some beats. So for example, the beats here these are beats where I have this wah, wah, wah in between these 2 peaks. So which of these then shows the 2 notes with the closest frequencies, A, B, C, or D? Just try that and see how y'all stand with that. Which of these shows notes with the closest frequency? All right, I'll stop at 40, and then we'll take a break. Okay, yeah, I thought. Didn't make a lick of sense to you, did it? Yeah, the right answer here is going to be C. I'm sorry, I don't think I didn't explain it very well. When I have these 2 waves come together, you can imagine that you have this repeating wave here and here. Those are like 2 beats. So here I have 1 beat, I have 2 beats. So the difference in the frequency for that wave is going to be 2 hertz. So F1 minus F2 for these 2 waves that made up this signal is going to equal 2. But notice over here I have 1, 2, 3 beats. So the difference in frequency is going to be 3. Here I have 1, 2, 3 beats, and then similarly here I have 3 beats. Does that make more sense? Let's take a break. I think we all need a break. It's 2:55. Let's take a 10-minute break, okay? We'll be back at 3:05. And then we'll move on a little bit more simple harmonic motion. Then we'll move into electrostatics. You all ready to get started now? We're almost done, okay? Just a little bit longer. Well, this 3-hour course is hard, huh? Is it hard for y'all sitting here for 3 hours? Yeah, me too. All right, a couple more things about sound. The Doppler effect and also intensity. When we talk about the intensity of sound, we usually talk about it in terms of decibels, and decibels is a logarithmic measurement. So for every decibel, you get a factor of 10 increase in the intensity. And the reason for that is because the human ear isn't sensitive enough to detect, like for example, a factor of 2 change in intensity, that it's more attuned to a logarithmic change in intensity. So that's why we use decibels. The intensity is power over area. That's why it's good to move away from very large things, because for every factor of 2 that you move away from something, it decreases the intensity by a factor of 4. Because we look at the area, so like if I have a source of sound here, as I move out, the area increases by a factor of 4 pi r squared. That's the area of a sphere. And so as I move a factor of 2 away, my intensity drops by a factor of 4. Because of this dependence upon the area, the surface area. A decibel, which is dB, is equal to 10 times the log of I over I naught, where here I is the intensity of the sound, and I naught is like this threshold intensity. Let's see, it is, I don't think we give this value here. No, this is the threshold. Basically, what is the smallest sound or the quietest sound that you can hear? Is there 2 H's in threshold? I don't think so. It's a threshold intensity. It's just the smallest sound that you can hear. Intensity is measured because it's power over area. Intensity has units equal to watts per square meter. Watts per square meter. All right? Yeah. Oh, because area of a sphere. Yeah, the surface area of a sphere, not of a circle. All right? Because sound emanates in 3 dimensions. All right. Let's see. We've already covered beats. Y'all okay with beats? It's just the number of beats is equal to the difference in the frequencies. Is that okay? All right. Also, the Doppler effect. The Doppler effect occurs when the source is moving closer or moving away from the observer or where you're detecting the sound. If it's moving towards you, it causes what change in frequency? Does the frequency increase or decrease? You'll probably observe this, right? If the source of the sound is moving towards you, what happens to the frequency? It increases, right? It's like a train coming towards you and it's blowing its horn. And then it moves away. That was really bad, wasn't it? But you know what I mean. That as it... What's that? An ambulance, right. So the frequency seems to increase as it's moving towards you, and then as it moves away from you, the frequency decreases. It actually gets a lower pitch. So it goes from high to low, high, low. Sorry, that's my little trick. The frequency, this is in your book, but the frequency observed, this is the observed frequency, is equal to the frequency of the source times V plus or minus v naught, depending upon whether it's moving towards or away from you, divided by v plus or minus v source. I'll describe what each. This is the velocity of the source. This is the velocity of the observer. All right, this is the frequency of the source. And then this is the observed frequency. Let's see, I thought we had a simpler form of this. Let me look at my notes real quick. What's that? Right, yeah, so if the, this can simplify a bit, where the velocity of the object, so this would be VO, divided by, this is the speed of the wave, so here this would be the speed of the wave. I'm sorry to change variables on you. That's the speed of the wave. So the velocity of the observer over the speed of the wave is equal to the change in frequency over the frequency of the source. That might be an easier thing for you to remember. It's a little simpler. All right? We'll try working some problems here in just a second. This is the Doppler effect, yeah. I said that, but let me write it. Let's work through a few problems. We'll go with the handout. I had some more in the practice test, which we'll come back to. So if you go to the handout that I gave you, let's look at problem number 756. This is an application of the Doppler effect. The speed of sound is approximately 340 meters per second. A police siren sounds at 1,000 hertz. A stationary observer hears the siren at 1,100 hertz. What is the speed of the police car? First of all, is the police car coming towards or going away from you? You hear it at a higher frequency, so is it coming? It's coming towards you, right? So you can get rid of a couple of options there right away. Oh, is the speed of the wave. Yeah, in this case, the speed of sound. Speed of sound, the wave. Do I need to come back there? Everything all right? Do y'all read the little jokes in the book? The Doppler effect is when stupid ideas seem smarter when you read them quickly. got 15 more seconds, y'all. 2:45. Let's shoot for. 2:45. Just a few more seconds. All right, 2:50. Just a few more seconds. We're still missing a few people out there. Or did we lose some people? 5, 8, 11, 17. All right. A is the right answer. Very good. You just have to know this formula for the Doppler effect, really. And I've seen it come up on a number of practice problems. So V over C is equal to delta F over F. And notice this is different from what's in your book. So, but I think it's easier to remember. V over C. V is the velocity that we want to know. C is the velocity of the wave. So it's going to be C times delta F over F. That's going to be 340 times delta F, which is the difference in the frequencies, or 100 hertz, divided by 1,000 hertz. That's 340 times 0.1, which is 34. Towards, we've already said it should be towards. All right. I think I had another problem here. Yeah, there we go. Let's try number 746 really quick. And then we'll move on to 747, just to illustrate a point. All right, I'll stop at 50. 50. Just 5 more seconds. Still missing quite a few people. No? All right. Okay, A is correct. What's the problem? Okay. All right, so the answer is A. Very good. Number 747, I'm not going to open it up as a clicker question, but it says the speed of sound in air is 340 meters per second. The sound from a jet moving from the air at 100 meters per second will still move at 340 meters per second. So the velocity of the source doesn't affect the velocity of the wave. It just affects the perceived frequency. Let's write that down. The velocity of the source doesn't affect the velocity of the wave, of the sound wave. It just affects the perceived frequency. Doesn't affect. You can think about it, if I have this plane that's coming along, I have this plane, it's emitting some sound. Right. The velocity of the waves are still the same, but because each time this wave comes out, it gets scrunched up with the next one, right? That as it's traveling forward, it emits a wave. It still travels at the same speed as the speed and the sound as the speed of sound and air, but they get scrunched together, and so the frequency is greater. Yes? All right. I think that's the end of sound. As I said, I will put some more practice questions online. Not this week. It'll probably be later in the week. But I'll have some practice questions for the upcoming exam, which will not include this material. It'll include just chapters 1 through 6. All right, let's move on to electrostatics. I will, yes. Yeah, so I'm going to try to get, well, on Monday I'll put up questions that you can practice for the exam coming up next Friday, on Monday, and then later in the week I'll get up questions for the next exam, which will be the following week. Is that true? No, it's not the following week. It's the following week after that. But I'll get you some practice questions though. Is that clear what I just said? I feel like I'm not making a lot of sense, am I?
Two tests in a row. Because we just Friday.
Oh, right. So we have an exam next week, but then that's our last physics day. And then the following week, we'll have an exam before you start organic. And Dr. Cortez is doing organic. Okay? All right. Let's look at electrostatics. So this is sort of beginning on the beginning of Physics 102. I have a couple things in electrostatics. First, just the nature of charge. Positive charges attract. Positive charges repel, actually. Excuse me. Like charges. What do? Like charges do what? They repel. And opposite charges attract. We can describe the force between two charges. So they have a charge Q1, I have a charge Q2. The force between those two charges is K, which is called Coulomb's constant, Q1, Q2, over R squared. This looks a lot like Newton's universal law of gravitation. We saw that back in chapter 3 or whatever, chapter 2. It's because it's an inverse square law. It's a field force also. The force on this charge, which I'll call F12, is equal to this charge, which I'll call F21. So F12 is equal to the negative of F21, or the magnitudes of those two charges are equal. That's an application of which of Newton's laws? The third law, right? So because I have equal and opposite forces. Let's see, K here, as I said, is Coulomb's constant. And K is equal to 9 times 10 to the 9th. It's in newtons meters squared per coulomb squared. Notice you can get that just from looking at the equation over here. I know that it has to be in those units in order to give me newtons for the force. I can also describe the electric field. The electric field is based on the force. So the electric field is equal to the force per unit charge. We talked about it in Physics 102 how we have this test charge. So if I have this test charge, which I'll call Q, or I have a charge here, and then over here I have a test charge, a positive test charge, I use this to sample the electric field, and this positive test charge will tell me the direction of the field. If this is a positive charge, the force felt by this positive test charge is in that direction. That's also the direction of the electric field. So the direction of the force is also the direction for the electric field vector. Right? Because the electric field is defined based on the force. The electric field is just a way of describing what is the force around a charged particle. The electric field is measured in newtons per coulomb. 1 Newton per coulomb is also 1 volt per meter. We'll see that in just a second. I'll describe how the voltage is actually related to the electric field. If E is equal to F over Q, then we can also get another expression for the electric field. Remember, F is KQQ over R squared. So you can imagine then that one of those Q's will cancel out, and I get this expression for the electric field due to a point charge, which is KQ over R squared. So I have 3 different things that come out of this. Coulomb's law, which describes the force between 2 particles. The electric field, which is just this definition of this field to describe the force. So the electric field is based on the force. And then I can calculate the electric field due to a point charge, which is KQ over R squared. But that's combining these 2 things to get the expression for the electric field. This jogging your memory from a couple years ago? A year or so ago? Some of you just had this. All right, so that's our electric fields. We can draw field lines. I haven't seen many field lines in the practice test though, but as I said, anything can happen. Field lines start at positive charges and they go towards negative charges, like that. Field lines will curve around. Field lines represent the force, so if I pick a point, say right here, and if I were to put a positive test charge right there, I can imagine two force vectors. I have a force vector due to this charge, which is in that direction, and then I have a force vector due to this charge, which is in that direction. And then if I combine those two forces, I get a vector that is tangent to the electric field line. So the fields describe the forces. The field describes the forces. And the direction of the electric field is going to be the same as the direction of the electric force. I can draw out these field lines. They'll look something like this. Y'all did a lab when you were in that class where you had to do this. Field lines go from positive to negative charges. Positive to negative charges. The density of the field lines represents the magnitude of the charge. So if I have, say, a +2 charge here and a -1 charge here, I will have field lines that come out like this. And then I'll have additional field lines that don't end. So over here where my field lines are closer, I have a larger electric field because the density of the field lines gives the electric field, the magnitude of the electric field. And when I have a bigger charge, I have more field lines because it produces a greater force. All right, electric potential. I go down from here. If I have a collection of charges, the energy, this is the potential energy, is equal to the work that's done in collecting those charges, which is equal, work is force times displacement, or I'll call it F times R. F is QE times R, which is going to be KQQ over R. So if I have a collection of two charges, then the potential energy contained within those charges is equal to KQQ over R. Right, these are just things that you'll just need to know. All right. The potential, this is potential energy. Actually, in your book, they call this E with a subscript P for potential energy. I'm going to call it PE. The voltage, so a couple different words that we'll use. We'll use voltage here. R, we might call it potential. R, when we're talking about the potential between two different points, we'll call it potential difference. And this voltage is equal to the potential energy per unit charge. So voltage is energy per unit charge. We measure this in volts. And 1 volt is equal to 1 joule per coulomb. I've seen a bunch of questions in the practice test that have to do with units. Whenever you're dealing with units, you just want to think about the equation. What is the equation describing this? And then you can plug back in and find out what are your basic SI units. All right. Let's do a few questions, and then we'll come back to a few things, a few practice questions. All right, let's look at number 762. I have the distance between two negatively charged ions is doubled, then the force on one of them due to the other will do what? If I double the distance, what happens to the force on those charges? If you finish that, go on to the next one, 766. All right, 105, I'll stop. 105. The answer here is D. You want to remember that R squared dependence, okay? Go back to F equals K QQ over R squared. If I increase R by a factor of 2, that will decrease the force by a factor of 4, all right? Because it's R squared. Go with me on that? Is this just a long day? Okay. You want to be okay on those. You want to be able to not just know the equations, but be able to tell when I change one variable what happens to the other variable. All right, what are the units of the constant K for Coulomb's law? I'll stop it. 28. 28. All right, very good. B. And if you ever forget the units, as always forget the units, you just look at the equation and ask yourself, what units would K be in order to give me F in newtons? And let's try this next one, 767. Which of these statements is true? If you finish that, go on to 770. We're going to do it next. I'll stop at 105. 105. Very good. C is the right answer. Electric field, remember, is KQ over R squared. And so that's an inverse square proportionality. So C is the right answer. Now let's look at number 70. This is 770. This is a little bit trickier. Which of these do not represent the units for the electric field? So 3 of these are appropriate units, and 1 of them is not the appropriate unit.
Is it, you think, a voltage or?
V is voltage, yes. Or volts, rather. The units for voltage. All right, I'll stop at 105. 105. Very good. I guess it wasn't that tricky after all, but let me show you. I've already told you that B and C are the right units. Those are correct units. Let's look at both A and D and see which one is correct. So y'all did put D, right? Is that the right answer? Yeah. So let's look at A first. So I have joules per meter per coulomb. So if joules per meter is the same as newtons, then that would be appropriate. Now joules, remember, is for energy or work, and work is force times distance over a distance, which is meters, so those would cancel. So this has the same units as force, just based on our definition of work. All right, so that is an appropriate unit, so it's not the correct answer, but D is the correct answer. All right. Let's look. Let me just work through number 773. I'll show you what the answer is because we haven't actually covered this. The voltage in a particular direction is equal to the change in the electric field times the distance in that direction. So here I have this charge that is moving from this point up to this point along a distance d, and it's moving across the electric field lines in that way. And I want to know what is the change in the voltage that's experienced by that charge Q. Now notice here that these have to be in the same direction. So when I write this as EX, that means the X component of the electric field times the distance in the X direction. So how does the distance change in the X direction via the EX? And so that comes about then. That's why this the correct answer is going to be E times D times cosine theta, because it allows for this this X component of the electric field, or the X component of the displacement, however you want to look at it. All right, and then that's going to be my change in voltage. So you want to know this expression as well, that my change in voltage or my change in potential is the product of my electric field and my displacement. But they have to be in the same direction. So you could, so they have to be in the same direction. So the component of that along the displacement vector. All right, let's look at 775. We haven't been working many of the practice tests, but a lot of the problems that I've pulled out are very similar to these problems, so that's why they've been just redundant. So in case you've wondered why I haven't been working those. All right, I'll stop at 130. 130. Okay, C is the right answer. Remember, a positive particle feels a force that's in the same direction as the electric field. That's how we define the electric field. So it's just by definition that that's true. So this positive particle will feel a force in the same direction as the electric field. So if I let it go right here, they sort of tell you about all this business. That doesn't really matter. You're just letting it go at this point, and then it's going to feel a force in that direction due to the electric field. Which of these is true about the electric field? It's least likely the result of which of these? And this electric field has parallel electric field lines, so it's least likely the result of which of these? We're almost done. You'll just hang in there. All right, about 5 more seconds. Stop at 58. The answer here is A. Why is it A? Why is it least likely the result of a point charge that's nearby? What do the electric field lines of a point charge that's nearby, what do they look like? They're diverging. So if I were to look at a point charge that's nearby, like right up next to it, my electric field lines are going to be all diverging from one another. But when you get really far away from that charge and you see those electric field lines, they're going to look parallel to you. Is that clear? As I move far and far away from it, I'm looking at basically lines that appear very parallel because I'm looking at lines that are really close together. As I move further and further away, I'm basically sandwiched in between lines that originate basically from the same point on the charge. All right. So a point charge nearby is not the result. Excuse me. This electric field is not the result of a point charge nearby. It could be either a point charge far away, a parallel plate capacitor, which we haven't talked about yet in this course, but we've all seen those, where I have two metal plates and the electric field lines run in between parallel to one another, or a very large single charge plate, which would also produce a similar electric field. So A is the correct answer, and let's do 780. This will be our last question, by the way. All right, 105, I'll stop. What's the question asking? Sorry. What is it? Yeah, so B is right. Oh yeah, so as you move away from the charge, the electric field decreases. It actually decreases a lot, right? Because E is KQ over R squared. All right, just a couple more things, but we're done here. So about the exam on next Friday, what's going to happen is you're going to come in, and just like we did before, Dr. Wayner, y'all did it, right? It's in the beginning of the class. You'll have an hour to take the exam. And I would expect about 25 questions or so. Some of them might be in passages, but then some of them will just be, questions like we've been doing. The way you study for it is, I'll send you out some practice questions. You can go over the practice questions that we've been doing, but I'll send you out some practice questions and you can work through those. I'll also put some tests up for you. Feel comfortable just doing that? Prepare? Yeah, I think that would be a pretty good way for you to prepare. All right. Any questions about it? Huh?
I was reading chapter 6.
Okay. What's up?
My first one was near section 612. It says that the constant should be memorized.
I'll send you an email when I get that stuff out.